Bipartite graphs, new section. It starts like this. Let r greater than or equal to 2 be an integer. A graph G whose vertex set is V and edge set is E is said to be r-partite if the vertex set V admits a partition into R classes. So that means you can partition V into disjoint non-empty sets which are R in number, so that their union is V, such that every edge has its ends in different classes. And that is why vertices in the same partition class must not be adjacent. So we will now try to understand this definition, but before that we have this small term instead of two-partite, because we are saying r-partite now, where r can have this smallest possible value 2, instead of two-partite we say bipartite. We usually say now, to understand the definition, we are given two graphs, two three-partite graphs. So let's just draw them and see how they illustrate the definition. So in the first graph, these are the vertices. Oh, there is one more. Okay. So in total there are 6 vertices, and this vertex set has been partitioned into 3 disjoint sets, subsets. One of them consists of these vertices, one of them consists of these 2 vertices, and one consists of this single vertex. And the edges in this graph are these. This is one edge, then we have a triangle here. This is another edge, this is another edge, and there are two more. We have this one and this one. So you can see that like what we have in the definition. The definition says that every edge has its ends in different classes. So that you can see happening here. Any edge you see has its ends in different classes, and that is why vertices in the same class are never adjacent, because if you have such an edge, then its ends will belong to the same partition class, which is not allowed by the definition. In that case, it won't be a partite graph, r-partite graph. So this is an example of a three-partite graph. And note one more thing, that what this definition says has a trivial case. It says that every edge has its ends in different classes. Now, if in place of this graph we had this graph, say, with no edge actually, that is also a three-partite graph. Why? That is because this statement that every edge has its ends in different classes is vacuously true in this case. Another way of saying the same sentence is that if E is an edge in the graph, then the ends of E belong to different partition classes, which is just one way of saying this implication. E is an edge in G implies the ends of E belong to different partition classes. So that means if there is no edge in G, if the hypothesis of this implication is false, the implication is vacuously true. So such a graph is also a it's a three-partite graph, sorry. So that case is there, included in the definition. And that is why you see that vertices in the same partition class must not be adjacent. None of these three vertices are, they are not adjacent. No two of these three vertices are adjacent. Here these two vertices are not adjacent, and here of course we have only one vertex, so no question of adjacency. And there is another such example. In this other example, it's also a three-partite graph, but we have partitions containing equal number of vertices, and the edges are all possible edges that are allowed by this definition. That means only these, for example, these two vertices cannot be adjacent, these two cannot be adjacent, and these two cannot be adjacent. Maintaining that restriction, every other edge is there. So this is adjacent to all the vertices except the one belonging to the partition class where the vertex itself is a member. This is adjacent to all these vertices except this one, because it belongs to the same partition class. Similarly, this one is also adjacent to all the other vertices except that first one. just like that. This one is adjacent to all the vertices except this one. Already we have made the connection of this vertex with these two. So we are left to draw these two edges. And the similar thing has to be done for this vertex. That means these two edges. And now we have completed drawing all the edges. It looks a bit messy, but it is just what it is. And you can clearly see which pairs of vertices are adjacent. So these are examples of 2 3-partite graphs. And in fact, there is a notation for this one. Let's just go through the discussion that comes after this, and then we will write the notation. Okay, an r-partite graph in which every 2 vertices from different partition classes are adjacent is called complete. In which every 2 vertices from different partition classes are adjacent is called, such an r-partite graph is called complete. It's like your ordinary complete graph, except that it cannot have absolutely all the edges. Maintaining r-partiteness, it has all the edges that it can have. The complete r-partite graphs for all r together are called the complete multipartite graphs. Called the multipartite graphs. Next, the complete r-partite graph, this graph k r1 complement star k, let's just write one more, k r2 complement star like this, k rn complement is it has a notation, is denoted by k r1 comma r2 like this. And in particular, if it happens that this r1, oh sorry, actually does not matter, but the author has in fact written n1, n2, nr. I seem to have swapped n and r, n1, n2, nr. If it happens that all these numbers, all these positive integers n1, n2, they are all equal, if all of them are equal and you denote that common integer by s, then we abbreviate this notation still to something much simpler. We abbreviate this to k s superfix r. Thus, KSR is the complete r-partite graph in which every partition class has s number of vertices, in which every partition class has or contains exactly s vertices. Okay, now a few words about this thing. Let's just see what this is. We may not remember what this operation is, but if you go back to one of the previous sections, in fact in the first section itself where we started all the things, there you will see, let me just keep this figure for the time being. In that section, in the first section, you will see we had something like this, an operation like this, G1 star G2. What this operation does is that it gives us a graph that can be formed with G1 and G2 in this way. Say you have G1 and you have G2. This is the graph obtained by joining all the vertices of G1 to all the vertices of G2. Okay. Now, at the same time, let's recall one more notion that we got, in fact there itself, that if you have a graph G, then its complement is the graph obtained by making the adjacent vertices in G non-adjacent and the non-adjacent vertices in G adjacent. So so with these two notions, now what does this represent actually? Let's first see what Kn1 is. Kn1, this is the notation for the complete graph, not complete r-partite graph, just simply complete graph on n1 number of vertices. So there are, say for example, if n1 is 3, then K3 is your triangle. So what will its complement be? Its complement will be just 3 vertices with no edge at all. So like that, this denotes n1 number of vertices, and that's just it. That's what this graph is. This is the complement of the complete graph on n1 number of vertices. Like for example, here before joining these edges, we had this only these 2 vertices. This will be K2 complement. This one will be K1 complement. This one will be K3 complement. And then what we do, we take, for the sake of simplicity, let us first consider Kn1 complement star Kn2 complement. So that is obtained by joining all the vertices in Kn1 complement to all the vertices in Kn2 complement. For example, here you have, that's not what ultimately will give this one, but we are talking about this one because this is the complete 3-partite graph. Okay, with some, if we just simply say complete 3-partite graph, then that doesn't mean anything. We have to say what the partitions are, or more precisely, how many vertices are there in each partition. That also we have to say. So this is K2. I have a tendency to write suffix to superfix, and this one is also K2 complement. So when we take their star, we join all the vertices here to all the vertices here. If we forget about this one, this partition class for a moment, then we have all the edges that we can possibly have, maintaining the fact that we cannot have edges between these 2 vertices and these 2 vertices. Now then when you take another one, K2 complement star K2 complement star K2 complement, then you already have this one. So you can treat that as one graph and then join all the vertices in this graph to all the vertices here in this K2 complement. And that's how also we can view this thing. If you form this graph in that way, because that's what it is ultimately, then it is K2 complement star K2 complement star K2 complement. Now this is the special case. In general, there can be any number of vertices in any partition class in an r-partite graph. In particular, if all these partition classes have the same number of vertices, like what we have here, here n1, n2, n3, all these 3 are equal to 2, and that 2 is S. So then this same notation, that is according to this notation, this is what? This is K 2, 2, 2. Then this same notation can be written more simply using another symbol, another notation, that is K2, 3. that superfix r, that 3, denotes what partite graph it is. That is, it's a 3-partite graph, and this suffix denotes the common number of vertices in each partition class. So that's why we are writing thus KSR is the complete r-partite graph in which every partition class has exactly s vertices. Just like that, K23 is the complete 3-partite graph in which every partition class has exactly 2 vertices. Okay. Now there is a reason for, for writing this notation. This notation, in fact, and that's what the authors say, it appears as a footnote. Let me write that here. Note that we obtain KSR if we replace each vertex of KR by an independent S set. We obtain KSR if we replace each vertex of KR by an independent S set, and our notation of KSR is intended to hint at this connection. Hint at this connection. So here what Diestel is saying is this: now that we have the notation for this thing, this complete r-partite graph in which the partition classes are of the same size, we can use the notation and write what this graph is. The second one. The first one also we can write, although it's not written in the text. The first one you can, oh no, we cannot write the first one in that manner because it's not a complete graph. There is no notation for this type of graph where the graph is not complete r-partite, because there are so many of them, so many of varied type there. There is no point in formulating a notation for each one. This one, however, is, I should write it here, but because of lack of space, let me write it here. K2, 2, 2, which is also the same as K2, 3, according to our notation. Okay, now here what is the author saying? Note that this last notation KSR is obtained, that graph, for example this one K23, is obtained if we replace each vertex of the ordinary complete graph KR by an independent S set. S set, recall, is a set having S elements. independent S set of vertices. Independent S set, we understand that we have to take an independent S set of vertices. So here what we are saying, we can obtain, for example, K23 from K3 itself. K3 looks like this. No? We replace each vertex with an independent S set. Independent means a set of vertices is independent if no two vertices in that set are adjacent. So we replace each vertex with an independent set of two vertices, and then we make all the possible connections. You can view, I probably should have drawn it a little bigger to draw your attention to one thing, and I should perhaps not draw it free-handed. You can see one thing from these two figures, this one and the one above it. It's like they are the same thing, but when you look at this using a magnifying glass, or this one is a magnified view of this, then you notice that these vertices actually on a close inspection turns out to be two vertices. Here also these turn out to be two vertices, and these simple edges turn out to be this somewhat much more intricate interconnections. So that's why you can see why this notation and this notation should look somewhat the same. This one tells us more about the graph because it has more information. We need something to tell us that these parts, each such partition class has two vertices. So that extra information we have decided to put here. But the fact is that this one and this one look similar. Okay, without being too rigorous about this similarity, they just look similar. So that's why the notations should also look similar. Okay, so that's what the author is saying, that we obtain K2R, K23 by replacing each vertex of K3 with an independent 2 set in our case. And that is why the notation has been made in such a way, and it is intended to hint at this connection. next we have kept this figure here because the above figure means not this one but this one shows an example of the octahedron. K23. We have already come across the octahedron graph in the fourth section. I think in that section we have that notion of connectivity, connectedness, those things. There we came across the graph which looked like this, somewhat. I forgot the exact thing. It looks somewhat like this. And on this side also you have a similar thing happening. This graph and that graph actually are the same thing. Okay, you go back to that example in section 1. I think it's section, in that section it's example 143 if I am remembering correctly. You go and you try to see that these two graphs actually are the same thing, only drawn in a slightly different manner. So that graph has that name, octahedron. And now graphs of the form K1, N are called stars. For obvious reason, because in K1, N what happens is that you have two partition classes. One of them has your one vertex and the other partition class has n number of vertices, and then you draw all the possible edges. Now this same graph can also be drawn in a somewhat different manner, like this. There are other edges. So this single vertex forms one partition class and the other vertices form the other partition class, and then you make all the connections, and this thing looks like star. Okay, so that is why such graphs are called stars. And this sole vertex which makes up one partition class, that is called the center of the star. These are called stars. The vertex in the singleton partition class is called the star's center. Now one more example is given before we go to the only result of this section. It is the graph K3, 3. Okay, a bipartite, complete bipartite graph. where both the partition classes have 3 vertices. I mean, each one of them has 3 vertices. Now, these are 3 different drawings of the same graph. One of them is, of course, this one. One partition class consists of these 3 vertices and the other one consists of these 3 vertices. So first I join the topmost vertex to all the vertices of the other partition class, then I continue that process with the other vertices. It is the same as this graph. Okay, I need to use the space somewhat more carefully. In this second drawing of the same graph, the vertices belonging to one partition class are like this. This one, and this one. So, okay, let us just to show that fact that these belong to different, I mean these belong to the same partition class. Let's just draw black circles and these are white circles. So this needs to be adjacent to all the white circles. Like that, this one needs to be adjacent to all the white circles. These 2 edges can be drawn neatly like straight line segments. The other one, however, needs to be drawn in this way. But before that, let me just join these 2 also, because this black vertex needs to be adjacent to these 2 white vertices and also this one. I am joining these 2 first because that's how it's given in the text, and this one needs to be adjacent to this. Now what the author has done, he has drawn like this. This gap indicates the fact that this is not an actual gap, okay, it just shows that this edge appears in front of this other edge. Okay, so that's I mean, you can understand, you have seen this type of things now in drawing lessons. And there is another way I have to generate a little space here of drawing the same graph like a hexagon, and here again these vertices belong to one partition class and these belong to another partition class. So these 2 will be adjacent, these 2 will be adjacent, and these 2 will be adjacent. Like that, we will have these 2 edges and this one, and finally these 3 edges. It just shows that if you are given a graph Okay, you may be given a graph which looks like this, or which looks like this, or which looks like this. They look quite different. However, we can clearly see that they are the same graph. There are three different representations of the same graph. So how do we know, looking at a graph, that it's a bipartite graph? It may be quite difficult to just look at a drawing of a graph and figure out that this is bipartite or this is not bipartite. Is there some sort of criterion for deciding whether the graph is bipartite? And there is one, and that criterion is the only result of this section. It's a necessary and sufficient condition. So this one, it has something written below it, three drawings of the bipartite graph. Because of lack of space, I will write that thing here. The graphs above are three drawings of the complete bipartite graph K3, 3. So this is K3, 2. There is a chance that someone will make a mistake in figuring out these two numbers. The one that appears as superfix, don't confuse yourself. You recall the notation for our complete graph. The superfix 1 is the one denoting partiteness. That is, r-partite means kr. Okay. And the suffix that appears below that one, that denotes the size of that each partition class. If all these things look confusing, you just think of that thing. You think of that thing. Okay, how one can get KRS from KR by magnifying each vertex. If you in the magnified view, a single vertex becomes an independent set of S vertices, and in that magnified view, each single edge becomes all those possible edges that are there between two partition classes. Okay, that way you can remember this thing. Okay, now comes the criterion for deciding bipartiteness. So the author writes in the next paragraph, clearly a bipartite graph cannot contain an odd cycle. An odd cycle is a cycle of odd length, or equivalently a cycle on an odd number of vertices. In fact, bipartite graphs are characterized by this property. Okay, so in this paragraph, the author is saying that clearly a bipartite graph cannot contain an odd cycle. We have to justify it, okay, which we will do, but not right now. A cycle of odd length. So what this statement means is that if we are given a bipartite graph, then it is guaranteed to not have any odd cycle. If at all some cycle appears in the graph, it must be an even cycle. Why, we will see, okay. But the converse is also true. That's why, in fact, bipartite graphs are actually characterized by this property. That is, a graph is bipartite if and only if there is no odd cycle, and that is the next result. Proposition 161. A graph is bipartite if and only if it has no odd cycle. It contains no odd cycle. Because Diestel has written that clearly one half of the proposition is true, so in the proof we have only the other half. This first half, which is clearly true, we will make it clear. Let's just first go through the proof of this, which will in fact have that part which says that if the graph has no odd cycle, then it has to be bipartite. That part is what the proof is about. So we start like that. Let G equal to V comma E be a graph without odd cycles. We show that G is bipartite. Okay, now in the beginning itself, we dispose of the situation where you can have multiple components in your graph, because you see the proposition does not say that the graph has to be connected. It may not be connected. So we in the next line, what the author says is this: clearly a graph is bipartite if all its components are bipartite or trivial. Components means connected components. We may assume that our graph G itself is connected. Because if we prove this thing for connected graphs, then those graphs which are not connected will have the components, and in the components, if they turn out to be bipartite, then the entire graph is bipartite. So automatically those graphs will, for those graphs also the result will follow. So it's enough to consider G to be connected. Okay, now if G is connected, then we can find a spanning tree in it by removing some unnecessary edges. You can create a spanning tree without removing vertices, because then you won't have a spanning tree. You can start removing edges in order to break cycles. That will give you a spanning tree. And in fact, we have already proved, recall, a much stronger result. In a connected graph, we can find not just a spanning tree but a spanning normal tree with any chosen vertex as the root. That result we have proved. Anyway, we will get a spanning tree. So let T be a spanning tree in G we don't need to consider normality of the tree or lack thereof here for this proof. We just need a spanning tree and we need to choose a vertex as its root. In G, and arbitrarily pick a root R to be any vertex in that tree. Then whether T is normal or not normal in G, that does not matter, but with respect to this root R, we have the tree order in the on the vertex set of G. Note that because the tree is spanning tree, the vertices have not been affected. Whatever vertices the graph originally had, they are also there in the tree. So on that vertex set, with respect to this tree T and with respect to the root R, we have the tree order, and we will denote that tree order with a notation and denote the associated tree order on V. On V by this. That order relation notation or symbol suffixed by T, it denotes the fact that it depends on the tree order in T arising from T and that root R. For each vertex V belonging to V, the unique path RTV, because T is a spanning tree, whatever vertex V you choose from your vertex set in the graph, there will be exactly one path in the tree starting at the root R and ending at V, a unique path, which we have seen this thing when we were studying trees. And that path will have either even length or odd length. Now, according to this disparity, based on this, we can in fact partition the vertices of T and hence all the vertices of the graph into two partition classes: those that are at an even distance away from the root R and those that are an odd distance away from R. R in particular itself is at an even distance away from R because the distance is 0. So it will belong to one partition class, of course. The unique path has odd or even length, which is of course the distance, has odd or even length, and this can be used. This defines a bipartition of V. Bipartition means a partition having two parts, two sets. A bipartition of V. We show that G is bipartite with this partition, this particular partition. Okay, now to illustrate the situation, there is a diagram, a graph, which is a particular graph, but it will be enough for us to understand the general case. So what we now have is our spanning tree with its root R, and then we will see what that figure shows us about the current situation. Now that figure I cannot properly draw here, there's not enough space, so let me just use this part. To show that bipartition, the author is using that thing that we did, that is using black circles and white circles. In fact, it's from this text that I have got the idea. So let me just first carefully draw this graph and then we will see where it leads us. Okay, somewhat in a risky manner, I have in fact drawn all the vertices and not a single edge, but I think I won't mess up. And then we have this one. Next, there is this sixth cycle. This edge, however, has been drawn a dashed edge, which you will see in the proof it may or may not be there. I think I have missed one vertex. We will see. Okay. Yes. One is here. Now, according to the proof, this cycle is CE, this edge is E, this vertex is X, this one is Y, and this is our tree T, of course minus this edge E, because otherwise it won't be a tree. And there is one more vertex is there. How many are there actually? This is our root R, this black vertex, and this is the white vertex. I think that's just it. Let me just look at the general structure. Yeah. The cycle CE in T plus E. Okay, now we continue the proof. So after this, there is this, let me just write from here. Let E equal to x, y be an edge of G. Edge of G, okay. So in the original graph G, we have considered an edge. So because this is an edge in the original graph, after that tree formation, by removing whatever edges you wanted to remove, this edge may or may not have survived in that process. So two cases will arise. It may be the case that some edge like this one or this one, for example, may have been removed, from the graph in order to form the tree. In that case, the edge E has survived and is now a part of the tree T. So that is this case. If E is an edge in T with x less than y, say, with respect to that tree order, then keep one more thing in mind. Recall that the tree order actually orders V partially, not necessarily totally. This order relation is a partial order relation on V. So if you take any two vertices, they may not be comparable. It may be the case that none of them is less than or equal to the other. However, if you take an edge, then its ends are always comparable. You go back to that tree order, that is in the section on trees, there you will see this thing explained. We have already discussed this. So that is why either x is less than y or y is less than x, because they are adjacent. Okay, so if this is the case, then r-ty, so if this is the case, then y, according to the terminology that we saw there in that tree section, y has more height than x. That is, if we are starting from the root r, then x comes after that y comes. And in fact, the unique path linking r to y first goes from r to x and then goes to y through that edge xy, that is E. Okay. So rty is in fact equal to rtxy. And so x and y belong to different partition classes. Why though? That is because you see, this rty actually determines whether the this path is even or not. I mean, whether it has even length or odd length. So whatever length this path has, this path also has that same length. Now a part of this path is the unique path linking r to x, whose length is 1 less than the length of this. So if this path has even length, this rtx path has odd length. If this path has odd length, rtx path has even length, and that is why x and y always belong to different partition classes. So that means if our arbitrary edge in the graph belongs to the spanning tree T that we have chosen, then its ends belong to different partition classes. Now comes the other case where E does not belong to T. Okay, if E is like this, then what happens? If E does not belong to T, then CE, which is obtained by joining the edge E to this xty path. For example, here you see in this figure, say this edge E, which we are representing with a dashed line, is originally not there in the tree. Okay, so here we have nothing actually. Now xty is this unique path joining x and y, this path. Now to that path, if we join this edge, extra edge E, then we obviously get a cycle. Now our hypothesis will be used. What is our hypothesis? Our hypothesis that the graph does not have an odd cycle. So this cycle must be an even cycle. So this is a cycle. And by the case already treated, the vertices are, okay, let me just write the thing. And by the case already treated, the vertices along txy, or I mean xty, xty alternate between the two classes. It should be a cycle that we have seen. Okay, now next part we are saying that this case where we consider the edge to be a part of the tree itself, there we have already showed that the vertices alternate between the two classes. That is, if you have along this xty path, if you have this vertex, for example, it belongs to one class, then because this edge E is a part of T, the other end belongs to another class, then again this edge is a part of T. So this end again belongs to the previous class. So like that, they will alternately belong to the two classes. Okay, now the evenness of the length of this cycle will come into play. Since CE is even, CE is, and we have this thing now, CE is even by assumption. X and Y will also belong to different partition classes. X and Y again lie in different classes. So regardless, and do you see why? You just look at this. This path has length what? The path has length, an odd length, right? 2, 3, 4, 5. I am only talking about the path, okay? Don't confuse it with the cycle. We are not considering the edge itself right now for the moment. On this path, we have odd length. because there are 6 vertices, the number of edges will be 1 less than that. In a tree, the number of edges is 1 less than the number of vertices always. So like that, on this single path, there are 5 edges, 1, 2, 3, 4, 5. Okay, so this belongs to one partition class, then this one comes, you get another partition, 1, then another one, 2, so you get the same partition, then another one, 3, so you get another partition. This one is black, okay. Black, white, black, white, black, white. Okay, so when we have 3, we have white. When we have 4, we have black. When we have 5, we have white. So you can see that if you are numbering the edges along this XTY path, starting from here and then going on numbering like that, then for every odd number, the other end will belong to the other partition class. So because your number of edges is odd, so that this final end will belong to a partition class that is not the one where this one belongs, and that is why X and Y belong to different I was saying congruence classes, partition classes. If we had evenly many edges, this would not happen. For example, if there was another edge, then you would get the same partition class, and that is why you cannot have an odd cycle in a bipartite graph. That thing that the author said is clearly true. That thing can be now understood from this, because if you have an odd cycle, then the odd cycle looks like this now. Again, it is after all a cycle, and the argument here will be like this. Say we have an odd cycle in a graph. If you suppose that this graph is bipartite, then this vertex will belong to one partition. It will belong to some partition, okay, one of the 2 partitions. This will belong to another partition. So this is your 1. Then this will belong to the same partition as this one. Why? Because it is bipartite. No? So this edge must have its ends in 2 different partitions, and because it is bipartite according to our assumption, so there are only 2 partition classes. So this already has belonged to a partition class. For specificity, let us denote the partition classes by A and B. Suppose you start your journey from here by assuming that this one belongs to A, then because this is an edge in your bipartite graph according to your assumption, this should belong to B. Then you go further down this path, again you come back to A, because this is again an edge and this already belongs to B, so this has to belong to A. So even number makes the vertex belong to A, odd number makes the vertex belong to B. Now what do you think will happen when you reach this one, this last edge, without considering this edge, for example, this last edge? Will this number be even or odd? Because the total number of edges available in this cycle is odd, so this will be even. This edge will be numbered using an even number, and even number leads that vertex to where? Again A. See, 1 leads the vertex to B, 2 leads the vertex to A. So if we end up with an even number here, this vertex will belong to A. But then the fact that there is already an edge between these two then directly contradicts bipartiteness. And that is why if you have an odd cycle, then the graph cannot be bipartite. So that is the other half which is not there in this proof, but which you can make a part of the proof by first starting with this and then doing this, or you can switch their places. And this completes the proof, and it also completes this very small section. In the next video we will see contraction and minors, some new notions. So let us end the video here itself. If you want to make some comments, you can use the comment section below, or you can mail me at my usual address. It will be there, the link will be there in the description. And today is Tuesday, so coming Friday we again have group theory from Herstein's topics in algebra. So with that, I am signing off from a mathematical room. See you on Friday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.